This presentation is an introduction to a paper by Nigel and myself with title Sashimi, Cutting Up CSI-FiSh Secret Keys to Produce an Actively Secure Distributed Signing Protocol. So, the idea behind threshold signatures is that we want to distribute the signing power among multiple users. So we have a set of n players, a threshold T, and we split the secret key into multiple pieces or shares, and then privately assign these shares to the players in such a way that any set of more than T players can jointly combine their shares and sign any document, while any set of fewer players cannot do anything. This way of sharing the secret key is called anti-threshold secret sharing, and the important case where T is equal to n-1 is called full threshold sharing. Classic applications of this include minimizing the effectiveness of such channel attacks at the level of physical implementation and securing cryptocurrencies transactions. How do we define security for a threshold signature? The mathematical idea to formalize this is by requiring that the signature output by a qualified set of players should look like if it were output by a single entity. Another way to look at this problem is that in a threshold signature, the secret key is never reconstructed in the clear, and this suggests we use multi-party computation. There are two ways of using MPC, either general MPC, where we compile the signature scheme with the MPC black box, and so the resulting signature will inherit security and other properties from the MPC engine, or we can have a specifically designed protocol. Here we need to prove everything from scratch, but this generally leads to more efficient protocols. This one is the approach we take in this work. A lot of work has been done to distribute signature schemes based on classic assumptions like discrete logarithms. A famous example is the standard ECDSA. However, discrete logarithms belong to a class of mathematical problems that we know to be that they cannot stand against quantum attacks, so we need to start looking at signature schemes based on post-quantum assumptions. There is a standardization process going on for this, but unfortunately all the candidate schemes seem to be very hard to do in MPC. At least for general MPC techniques, this difficulty comes from a number of aspects. The use of hash functions that were not implemented, were not designed to be executed over secret shared data, mixture of bitwise and algebraic operations that require different MPC techniques, and while switching between them is still not practical. And even when they show a very simple algebraic structure, however, they adopt large parameters, resulting in a number of secure multiplications. However, there is another mathematical problem that we believe to be post-quantum, but did not appear in the NIST competition for signatures, and is related to isogenies of elliptic curves. The first signature scheme based on isogenies was CSI, but was not practical, and it used rejection sampling, which is not very clear how to do in MPC. Luckily, last year it was proposed a new signature scheme called CSI-FiSh that improves the previous one in a number of ways. First, in efficiency, but most importantly, it avoids completely the use of rejection sampling. So becoming very similar to a classic Schnorr-like protocol. Motivated by this, in this work we propose a specific multi-party protocol that implements a threshold variant of the CSI-FiSh signature scheme. So we are using we are using a threshold secret sharing, and our protocol is secure against malicious adversaries in the setting of dishonest majority. It also has some limitations. Efficiency is one of them, and we cannot, and it's only secure in the standalone model. So our result is just is mainly foundational. As I said, CSI-FiSh is based on isogenies. We know that for a supersingular elliptic curve defined over Fp, the endomorphisms with coefficients in Fp form a ring which is isomorphic to an order of an imaginary quadratic field, let's call it O. And using some standard facts from the theory of arithmetic of elliptic curves, we end up with an action of the class group of O on the family of elliptic curves over Fp with the endomorphism ring isomorphic to O. Then we have the group action inverse problem, which basically says that this action of the class group is actually difficult, hard to invert. For cryptographic reasons, we will specialize that this elliptic curve is zero, given by the equation y squared equal to x to the third plus x. And that's because the class group has a very simple description. It's a cyclic group of order n, and therefore we get an action of the integers modulo n on the elliptic curves in the isogeny class of E0. And the gate problem becomes more explicit because now given two elliptic curves in the isogeny class of E0, the problem is to find a secret integer that connects them. With this hard problem, you can build several cryptographic primitives. Here is a Sigma protocol that allows a prover to prove knowledge of a secret integer A acting on the elliptic curve E0. It's very similar to a classic Schnorr protocol, except we don't have a group structure in the set of the elliptic curves. Using Fiat-Shamir, you can make this non-interactive. And we will also use a very standard way to compose Sigma protocols that gives you proof of knowledge that two isogenies connecting two pairs of elliptic curves are actually the same. Again, we will only use the non-interactive version. In Fiat-Shamir, if you hash a public message, then you get a signature on it. This is basically how the CSI-FiSh signature scheme is derived from the previous identification protocol. So if we want to distribute this, we want to do this in MPC, then there are exactly two values that need to be kept secret during the signing process. First is the secret key, of course, A, and also the uniform integer B. So all the operations involving these two values need to be done in MPC, which basically means step 2 in the key generation algorithm, which is the group action of A on E0 given the public key, and step 1 in the signing algorithm, which is the group action of B on the elliptic curve E0. So most of the job is just is computing a group action of a secret shared integer on an elliptic curve. Unfortunately, we cannot parallelize this operation. This is because we can't from the local actions xi and of xi on E and xj on E, we cannot derive the action of their sum on E, unless you already know xi or xj, but this is prevented by the gate problem. So we need to design a sequential protocol. Therefore, the communication will scale linearly on on the number of players, which is not good. Also, because we are dealing with malicious adversaries, each party needs to append a proof of correct computation. Also, to make sure that all the operations are carried out in the correct order, the players are required to hash what they are broadcasting. So we are using a general replicated secret sharing scheme, which is a very general method to get linear secret sharing starting from any monotone access structure. And monotone access structure is defined by two families of sets of players, the unqualified, qualified set of players. And these two families come with a partial order in them. And they are also complementary to each other, meaning that a set of players is either qualified or unqualified. You can define the family of maximally unqualified sets. Intuitively, this family, a set in this family is an unqualified set with the property that if you add any player that wasn't already there, it becomes automatically qualified. And from that, you can define this new family B, which consists of the complements of the sets in M. This family will parameterize our replicated secret sharing. To share a secret ring element S, a trusted party samples uniformly random elements SB, one for each element in B, so that they sum up to S. Player I receives the share SB if and only if it belongs to the set B. It's not difficult to see that each player will miss at least one share in this process. Also, in general, they will hold vectors of shares. And reconstructing the secret is straightforward once the parties agree on a qualified set of players. Replicated secret sharing is preserved under linear operations, so they can be performed locally. And you can basically realize anything with this, although not efficiently because you need to pay a huge overhead. For instance, you can get a anti-threshold secret sharing by just defining the qualified sets to be those with more than T players, and then apply the previous construction. There is an easy way to pass from replicated secret sharing to full threshold secret sharing. And the observation is that only a qualified set of players will participate in an operation involving the secret. So let's assume we have a qualified set of players who holds replicated secret sharing of a secret S. Then we rearrange the shares of S in such a way that each player in Q holds exactly one share of S. This way, we get a full threshold sharing over the set Q. This is not exactly as starting with the full threshold sharing in the set of players. The reason is that you need to take into account the shares that were held simultaneously by different parties. This probably is the trickiest part when you in the security proof of our protocol. But in my exposition, I will treat this as a method to reduce any linear sharing to full threshold secret sharing. And this is the functionality we want to realize in MPC, and also describes the main properties of our protocol. So the secret key is shared among the parties and then used to generate the public key. When the functionality receives a message, it outputs a signature on it like any normal signature schemes. And it also describes the adversarial model, because we are allowing the adversary to intercept all the public messages, to modify his own shares, and we are also giving him the the possibility to halt the signing operation at every stage. This captures the fact that we are designing our protocol to be secure against malicious adversary and possibly to abort if something goes wrong. Now, suppose we have a qualified set of players, P1, Pt, that want to compute the action of a secret share integer on the elliptic curve is0. Using the method I described before, we can assume that S is shared according to a full threshold secret sharing over Q. Let's call the shares S1, St. So the protocol for computing this action is organized into different rounds of computation. In the first round, each player individually commits to his secret share Si and then produce a proof, an interactive proof that he did use Si. Then he will broadcast both the result of the action and the corresponding proof to all the other players in queue. This step is merely needed in the security proof because we need somehow to force the adversary to commit to his share and then to provide a proof of knowledge so that we can extract his shares by, for instance, rewinding. The second round is where the actual computation of the group action takes place, and the first player, P1, starts by computing E1 from E0 using his share S1. Then he will produce a proof that the Si is using is exactly the one as he committed to in the first round, and then we'll broadcast both E1 and the corresponding proof to the next player, P2, who will do exactly the same, until the last player in the qualified set, Pt, will compute Et and a corresponding proof, and will send both to all the other players. If everyone in the qualified set in this protocol follow the rules correctly, then Et is going to be equal to the action of S on E0. If we plug this into the CSI-FiSh signature scheme, we get the protocol we wanted. So the players first start by generating a replicated sharing of a secret integer A, which will be the secret key. And then they agree on a set of players, qualified set of players P1, Pt, so that they can now represent A with a full threshold sharing on Q using the method I described before. And then they will engage into the protocol to compute the group action of A on E0. And the result is the public key. To jointly sign a document M, again, the players will first choose a qualified set of players, then each player Pi will sample a uniform integer Bi, and by doing so, the players will implicitly define a full threshold secret sharing of an integer, uniformly random integer B. And then again, using the protocol for the group action, they will compute the action of B on E0, and the result will be hashed along with the message. This operation is done in the clear, so it can be done locally by each player. So then each player again will compute an integer Ri using his share of B and the shares of the secret key. And this again will produce a full threshold sharing of an integer R, which is then reconstructed in the next step. And then the integer R and the hash value C are returned as signature on the message M. So in order to simplify the exposition, I omitted some details, and also I did not include the security proof. But you can check these things out in the full version of the paper, which is available on ePrint with the number 2019-1360. And I guess that was all.